and get started. Couple of quick questions though. Can you tell me what the derivative of cosine 7x is? Chain rule, right? It's a composite function. Chain rule says we find the derivative of the outside. Outside function is cosine, so that's going to be negative sine. Leave the inside alone, times the derivative of the inside. So this would be negative 7 sine 7x if we wrote it like that, right? Okay. So this is just going to be e to the tangent x, and then we're going to times that by the derivative of tangent, which is secant squared. Got to have them memorized. Okay, certainly don't want to derive every one of those. Okay, so there would be the derivative of that. Again, derivative of the outside, leave the inside alone, times the derivative of the inside. Okay, another one. That is 3 of them. What's the outside function? Outside function is the square root. Derivative of a square root is 1 over 2 times that same square root times the derivative of whatever we were taking the square root of. So that's a sine function. So that's going to be a cosine. Leave that inside alone. And then finally, times it by 4. And then we'd want to clean up just a little bit. I'm going to cancel this with that. That's going to be a 2. So we're going to have 2 cosine 4x over the square root of sine 4x. But again, the nice thing about writing it this way is you can see a big long chain of derivatives. We had 3 nested functions here. So you can see the derivative of a square root right here. You can see the derivative of a sine right here. And you can see the derivative of 4x right there. Okay? All right. Now, what's the derivative of 4 to the x? Okay. It's a little unfair to ask this. Unless you're a great student, you pay attention to everything, you just soak up every word, remember every phrase. Okay? People struggle with stuff like this. Okay? They struggle with trig functions, they struggle with logarithmic differentiation, and they also struggle with exponentials. Okay? If it's exponential base e, it's a piece of cake. Okay? If it's base 4 or base 7 or base 19.1, for some reason, it's more difficult, but it doesn't have to be, okay? The derivative of an exponential, exponentials are really cool. They are part of their own derivative. Every single one of them will appear again in its derivative. So the derivative of this exponential is that same exponential times what? Times the ln of the base, times the ln of 4. Okay, so we have this extra factor of the ln of the base. They're all related to the natural log, or excuse me, the natural logarithm or exponential base e. They've all got that factor floating around in there. And then times the derivative of whatever we plugged into that exponential, which happens to be an x. So its derivative is 1, so I don't have to write it. So I could just write 4 to the x ln 4, okay, and call it good. Okay, right. Yep, it is. Okay. Any questions? Okay, and any combination of stuff that we've talked about already. So we could have something like this. This would be horrible, but we could have 4 to the sine x. You could do e to the x sine x. 4 to the e to the x sine x. Okay, this is a exponential function, and what is the inside? It's a product. You'd have to use a product rule to figure that out. Okay. But given enough time, you ought to be able to do that. Okay? And enough practice. We haven't practiced a whole bunch with exponentials yet that are bases other than e, but we'll get there. Okay, everybody good there? Any questions on any of those? Just examples. This one right here? Okay, so this is exponential base 4. So it's 4 to the e to the x times sine of x. ln of 4, and then times the derivative of that stuff there. So that's going to be the first times the derivative of the second, whoops, cosine, plus the second times the derivative of the first. We can maybe take out an e to the x, clean it up that way. And there may be more than one way to do that one. Okay. So again, the quiz that you're going to take tomorrow and the test that you're going to take in a couple of weeks, you're just going to be given a bunch of functions and, hey, find the derivatives. Okay? And it's not too terribly bad to practice something that you were just taught earlier that day or the day before. And they're all the same type. Like, in 3.2, it was all product rule and quotient rule. In this section, it's all got something to do with the chain rule. In that first one, it was power rule and stuff like that. So when you mix them all together and you have to figure out, holy cow, what is this? What rules apply here? And what if more than one rule applies, what rule do I use first? Okay? All right. So let's come back here and let's pick up where we left off. We left off right there. Okay? So on that one right there. So let's see, 5 to the tangent of x. 5 to the tangent of x. ln of 5, derivative of tangent, secant squared x. Can't really do anything with it, right? E to the 4x. Okay, now again, I did one of these yesterday this way. I did one with an exponential base e this way. I realized the answer is 4e to the 4x. But what if we think about it this way? Okay, if you were going to remember a derivative rule for exponentials, you should remember that the derivative of an exponential is that exact same exponential times the ln of the base times the derivative of whatever we happen to be plugging into that. So the derivative of this exponential is that exact same exponential times the ln of the base times the derivative of what we were plugging into that exponential, which is 4x. So the derivative of 4x with respect to x is 4. So then we run through here, and this represents all of that rule that we were just talking about. We want to clean this up. The ln of e is 1. That's a 4, so we're probably going to write the 4 as a coefficient out front, and we get this. And again, that's the beauty of this type of mathematics. You get far enough along here, yeah, things get complicated, but the more complicated they are, the more ways there are to do the same thing. And if they all match, well, isn't that great? Okay? So this, in some respects, is a little bit of a silly way to think about this problem, but it does illustrate the point. If you were going to remember one of two rules, okay, the derivative of e to the u is e to the u du dx, or the derivative of a to the u is a to the u ln a du dx, which one in the long run covers everything? This one right here does. Okay? Yeah, it makes this special case a little bit longer, but at least it's got the right idea and it would take care of all of them. Okay? Any questions? Okay, so let's keep rolling along here. We've got this one right here. Again, an example of three nested functions here, a composite within a composite. And we peel off the derivatives one at a time. So this is going to be 1 over 2 times that same square root. Whoops, 3y minus 4. Negative sine 3y minus 4 times 3, right? And then again, all you're going to do is just clean this up to a reasonable degree. So I'm going to write a negative 3 sine 3y minus 4 on the top, and a 2 square root cosine 3y minus 4. Again, please don't do anything crazy thinking, my gosh, I've got to simplify this. This has to look better than this. You certainly can't cancel the 3y minus 4 with the 3y minus 4. It's an argument in the sine and the cosine, and you certainly couldn't make that a tangent or anything weird like that. So don't try any of that. As ugly as that is, that's the answer. Okay? Okay, take a good look at this one. Yeah, we could write it as something to the 1/3, or let's keep in mind what goes on here. And I have this example on here for a reason. For some reason, when we've got these squared trig functions or cube trig functions or something like that, we kind of forget really what it means. So let me show you what this means. So the suggestion from Ben is, let's write this to the 1/3 power. But let's remember what this means. This literally means, it doesn't mean you square the sine and then plug the angle in. It means take 3e to the 2x minus 4, take that and square it. Find the answer to this sine function, square it, then take the cube root, or then raise it to the 1/3. Now, this is not a great way to write it. That's a better way to write it, but what's the best way to think of this? To the 2/3, okay? Think of it as one single power rather than two separate ones. So we're going to write it this way. So the original problem is going to be, we're going to find the derivative with respect to x of sine of, 3e to the 2x minus 4, all of that raised to the 2/3. And then let's take a good look here. This is definitely a composite function. How many functions are there here? I mean, if we didn't get too crazy. Okay, at least 3, okay? We've got this power function on the very outside, okay? Then we've got a trig function. Then inside here we've got a sum of two functions, one of which is an exponential. So we've got an exponential plugged in here at the very least, okay? And then we've got a 2x plugged in here. So really, if you think about it, there are at least 4, okay? So 2x gets plugged into e, times by 3, subtract 4, okay? So there are two functions right there. There's a third one, there's a fourth one. So we're going to peel these off one at a time. And imagine, if you think about the technique that I showed you at the beginning, introducing that linking variable u, think about how many linking variables you'd need here in order to represent those 4 functions. You'd need 3 linking variables, because if we've got 4 different pieces, there's got to be a linking variable in between those 4 pieces. So you'd have to have 3 of them, okay? So it gets a little bit complicated doing a problem using that technique. That's why I like this derivative of the outside. 2/3, that same stuff raised to the negative 1/3. So I just write that stuff down here. Then peel that next derivative off. The next function was a sine function, so that's going to be cosine 3e to the 2x minus 4. Then I'm finding the derivative of the inside. The inside is going to be, help me out here, what do I get if I find the derivative of 3e to the 2x minus 4? Okay, so it's going to be 6e to the 2x. And that's it, right? Where'd the 4 go? Derivative of 4 is 0. What we did here is we said this would be 3 times the derivative of this, which is e to the 2x times 2. So we multiplied those together and got 6. Got it? Okay. Now, can we clean this up? Yeah, if you had to evaluate this, we'd probably do something like this. Now notice on the top, if I think constants, I've got a 2 and a 6, so I've got a 12 on the top. I've got an e to the 2x on the top. That takes care of this, this, and this. And then I've got a cosine of 3e to the 2x minus 4. Okay, so there's the numerator. And then I'm going to have a 3, and then this stuff raised to the negative 1/3 is the negative, we'll put it in the denominator. And this is going to be a cube root of the sine of 3e to the 2x minus 4. Okay, and as ugly as that is, that's it. Yeah. Okay, so let's take a look at the top. Okay, this has a negative exponent. Okay, so I'm going to take that, I'm going to move it in the bottom. We'll kind of get rid of that for right now. I've got a 2, I've got a cosine of this stuff, I've got a 6 and an e to the 2x. So 6 times 2 is 12. I've got this factor of e to the 2x, so I'll put that right there. And then I've got this cosine of 3e to the 2x minus 4. Okay, so that's on the top. Then I'm going to take this stuff, because it's got a negative exponent, I'm going to put that on the bottom as a cube root, and the 3 was already in the denominator, so I just leave it there. Okay? Yep. Questions? Okay. Okay, and I mean, at this point, we're just kind of playing around, aren't we? Okay, we've done enough practice here. It's just, I mean, could we go through all the infinite number of different combinations of functions that we could have and apply the chain rule? I suppose if we had an infinite amount of time, we could, but all we're doing now is just looking at the same type of problems, all chain rule problems, all composite functions, and we're just looking at, well, how would you do these? So these are a couple of interesting examples. So like I said a second ago, when you've got a trig function raised to a power, you just need to think about what it means. These two look very similar. Both have a sign, both have an x, both have a fifth power, okay? But they have completely different derivatives because of the way they were plugged into different functions. I've got a power function, the fifth power function, and I've got a trig function. I've got the sine function, okay? On this one, we really ought to think of it this way. This is the sine of x raised to the fifth. Sine is the inside, the fifth power is the outside. On this one, we don't need to rewrite it. You can see the fifth power function was plugged into the sine function, so they switch places. So on this one, if we find the derivative of the outside, it's going to be 5 times something raised to the fourth. And what is that something in this particular case? Okay, whoops, sine. And the derivative of the inside? Cosine. Now, I suppose you could leave it this way, but again, kind of standard procedure is to write it like this. Sine to the fourth x, cosine x. Okay. And on this one, when we find the derivative of the outside again. So the derivative of the outside here is cosine. Leave the inside alone, and then times it by the derivative of the inside. So that's going to be 5x to the fourth. Probably wouldn't leave it that way. We'd probably think of this as a coefficient. So we've got 5x to the fourth, cosine x to the fifth. And that's probably how we'd write our answer. Any questions? Okay. So this is just kind of a challenging problem to look at and think, okay, are you working out that part of your brain that allows you to compartmentalize and think, okay, all I need to do is worry about this one piece at a time. That's one of the nice things about the chain rule. Even though it differentiates very complicated functions, even though some of the answers look really nasty, the nice thing about it is we look at it and we figure out what's the inside, what's the outside. No matter how complicated the inside is, we're just finding the derivative of the outside and we're leaving that ugly inside alone. So what is the very outside function here? Yeah, it's square root, okay? So if I were to cover this up right here, whoops, if I covered that up right there, it's the square root of whatever that blob is, okay? So the square root of some blob is 1 over 2 times that same blob, right? Square root of that same blob. So this is going to be, and I'm going to just put an arrow here. So this is going to be 1 over 2 times the square root of x plus square root x, right? That is the derivative of the outside. I have left the inside alone, and now I need to find the derivative of the inside. So I'll do times the derivative of the inside. I've got more than one term here, so I'm going to start with a set of parentheses. And I just need to look at this inside. I'm literally just looking at this stuff right here. That's all. Okay? I don't care about anything else on there. I just want to find the derivative of x and the derivative of square root x, and I'm going to add those two together. So this is going to be a 1 for the x, and this is going to be 1 over 2 square root x for the other one. That's it. Is it cleaned up, though? Okay, we can clean it up a little bit, and here's where the problem comes. Most of the problems that we'll be doing, there's a little bit of calculus, and there's a whole bunch of algebra and trig and properties of exponents and different things like that. Okay? So we certainly don't want to just leave it like this. So how would we clean this up? Say that again. Just slide this over and put it on the numerator. Okay, we could do that. We could write it as 1 plus 1 over 2 square root x over 2 square root x plus square root x. Okay, you could do that. Would we leave it that way? Weston would. Okay, normally we don't leave things as complex fractions. It's okay if they look pretty ugly, but we normally don't leave a fraction in the numerator or the denominator of a fraction. So this is a complex fraction, so we want to clean this up. So does anybody remember how to clean this up? Nope, good guess. get a common denominator. Okay, when you've got a complex fraction, when you've got one of these big fat horizontal fraction bars, break it into a top and a bottom. Think of the top as one single problem, get a simplified answer for that. The denominator on this one, as ugly as it is, there's really not a whole lot that we can do with that. So what we're going to do here is we're going to get a common denominator. So I'll multiply that one by 2 square root x. So this is what I've got. I've got 2 square root x plus 1 over 2 square root x over 2 square root x plus square root x. And if you need any help, what if we had this problem right here? 1/2 divided by 3/4. Do we ever divide by a fraction? Nope. Flip the bottom one over and we multiply. So you got to think of that one as a fraction. You've got to put it over 1, or at least think of it as over 1, so we can flip that over and multiply. So when I take this and I flip it over, here's what I get. I get a 1 on the top. I get a 2 square root x plus square root x in the denominator. Okay? So the numerator is 2 radical x plus 1 over 4 radical x times radical x radical x. You could. It wouldn't be the end of the world if you did this. I'd be okay with that. It would be nice if you could do one more thing with this. This is 2 radical x plus 1. And then if I have a square root of, well, let's say I had something like this. Let me come up here and write down this problem. Let's say I have the square root of 3 times the square root of 6. Yeah, you slide them underneath the same square root, right? So let's do the same thing here. So let's put this as 4 square root of, if I slide that underneath there, it's going to be x times x plus square root x. That wouldn't be that bad. If you wanted to write this as x squared and then x times the square root of x, that would be okay. But that's about as simple as it gets. Can you cancel the 2 and 4 as tempting as that might be? Please don't. All the time we'll be doing a problem in calculus. We'll be finding a derivative. And we kind of lose track of this while we're going through the rules. But literally, that represents the slope of the curve at a point. So if I plugged in a number, let's say I plugged in the number 1, it would tell me the slope of the curve there. So if you make a silly mistake like canceling a 2 with a 4, which you cannot do here, your slope is wrong. Okay? So that's why the algebra and the trigonometry is so important. Okay, any questions on those? Yeah, you couldn't cancel them because, now say that again?
If that was underneath the radical, so if it was 2 radical x plus 1.
Yeah, then you could. Yeah, because then the 2 would be a factor of both the terms. You can't pull a 2 out of both of them and then have a factor to cancel with here. Okay, all right. So we'll run through just a quick example right here, just to kind of illustrate the point of how useful the chain rule is and that it really is the rule that we use most often. You can apply it to every single function, even something as silly as this one right here. We know the answer is 2x, but think of it this way. This is still a composite. X got plugged into the squaring function. That's what happened. X got plugged into the squaring function. So let's find the derivative of that. The derivative of the squaring function is 2 times whatever we squared. We leave that alone. Raise it to the first. And then we times it by the derivative of whatever we plugged into the squaring function. What's the derivative of x with respect to x? It's a 1. So very silly way to do this problem, but it does illustrate the point that we still get the same answer if we think of it using the chain rule. Okay? And then I think this is the last little bit. This is number 65. Again, this is a good thing to check and make sure that you understand what's going on here. How are these things related? Okay? We did problems like this when we were doing product rule and quotient rule. We looked at graphs and we figured out, okay, you've got to have the derivative of the first times the function value at the second, and then the derivative of the second, function value of the first, and all that sort of stuff. And we looked at the points here. We're going to do the same thing on this one. So this one says u is f of g, and v is g of f, and w is g of g. Okay? So what it wants us to find is u prime of 1, v prime of 1, and w prime of 1. So I'm gonna do different colors for each one of these. And the first thing that I would recommend doing on something like this is, rather than looking at the problem and trying to figure out what it is, just write down what the rule is. So the rule on this one right here would be, so u prime of x should be equal to, well, it's a composite. So let's do this symbolically. G got plugged into f. So what's the outside function? F. So the rule says, the chain rule says, we find the derivative of the outside, leave the inside alone, and then times it by the derivative of the inside. And then we don't want to lose fact of what these mean. This is the derivative, the slope of the curve at that particular point. This is the slope of the curve f at that point right there. So we've got to figure out what those are. So let's run through and do this. Now let's plug in the 1, so u prime, and my primes always look like 1s. I apologize. I should make it look like that. Okay? So this is going to be f prime at g of 1 and g prime of 1. Okay, well, let's work backwards. Let's come over here and let's figure out what is g prime of 1, because that's pretty easy. G is the blue graph right here, okay, that V-shaped graph. And it says, what is g prime, or in other words, the derivative? What word would we use? Slope. What is the slope at 1? So let's look right here. Here's 1. Let's come up on the blue graph. We really don't care that the function value is 3. What we care about is, what is the slope? -3. Okay, so this right here, the slope there is -3. Let's look at this right here, because we really need to do this in stages. G of 1. I come over here to 1. I'm interested in the graph of G. Now what am I interested in right here? The point, the function value. What is the function value there? 3. So we need to find f prime at that particular point. So notice how this swings us over where? We want to find the slope of f when x is 3. So we're right here. That would be right there. We really don't care that it's about 3.8 or something like that. What we care about is we want f prime at 3. We want the slope. And what is the slope? Yeah, down 1 over 4. So this would be about 1/4. Okay. Now take a good look here. Thank you very much. Okay. Again, don't make a silly mistake like that. We went down from left to right. Everybody knows that the one that goes down from left to right would be a negative slope. Okay. We want to make sure we get that right. So the answer here is 3/4. Okay. So see how even in this problem, we kind of peel this off a layer at a time. We do it step by step. Any questions? Are you sure? Got it? We found the slope at x equals 3. Yep. All right, so let's take a look at the next one. So let's figure out what v prime is. V is g of f of x, so that's going to be g prime of f of x times f prime of x. Okay, so let's figure out what these two quantities are here. Let's figure out g prime f of 1 times f prime of 1. So let's figure out what f of 1 is. F of 1 is 2, so that's going to be g prime of 2. And then I want to know what f prime of 1 is. F prime of 1, so let's see. That also, oddly enough, is 2. Why are they both 2? Why is f of 1 2 and f prime of 1 2? Let's do this one first. Why is f of 1 2? Because you plug in a 1, you get out a 2. Because the point is 2. The function value there is 2. Why is f prime of 1 2? Because the slope is 2. So on this particular one, both the value of the function and the slope of the curve at that particular point are both 2. Okay? So now I need to figure out what g prime of 2 is. So I go to 2, and I want to figure out what g prime right here. Okay? does not exist. Because this is a what? Corner. Okay? Corner or cusp, whatever you want to call it. Okay? So if I take something that doesn't exist and multiply it by 2, what do I get? A 2 that doesn't exist. Okay? That derivative does not exist. Okay? And the reason it doesn't exist is because the derivative of g doesn't exist at the point of interest at 2. Any questions? Okay. Can you do the last one? Okay. While you're doing the last one, see if you've got any questions on anything that we've covered so far, because again, we've got a quiz tomorrow. Covers everything up through and including 3.4, up through and including the chain rule.
Yeah, you get done with like 1/7.
Did you just ruin it for everybody?
Oh, what I said was.
Okay, so derivative of the outside, derivative of g, leave the inside alone, which happens to be g, times the derivative of the inside, so g prime here. Plug in a 1. I need to know what g of 1 is, so let's come over here. G of 1 is 3, so I need g prime at 3, and I need to know the slope at the slope at 1. That's going to be -3. We good with that? So I need to come over here and let's find g prime at 3. So if I go over to 3, I want this slope right here. This looks to be a run of 3 and a rise of 2. So the slope there is positive 2/3. We make sure we get that right. Cancel those, so we end up with a -2. Is that right? Okay, any questions? Okay, is there anything you want to see anywhere from 2.8 all the way up to 3.4? Okay. On the quiz tomorrow, I probably am not going to have you do something from the definition. It would probably be applying the rules that we've learned. Because if you think about it, wasn't there a problem on the first exam that had you use the limit of the difference quotient? Gosh, that was all of 2 weeks ago. Long time ago. Yes, there was. Okay. So you still need to be aware of how to do that. It's possible that they could put something like that on the final exam. In the past, they've done something like maybe that was one of the ones that they could choose. I have heard, I don't know whether or not this is the case, they're going to get rid of those sections where you can choose. They'll just say, hey, here are the 15 problems you need to do, and everybody has to do the same ones. Okay? All right. So any questions? Too many people gone. We'll do it tomorrow. Does that make you happy? No. Yeah, it is due Monday. It is. Yeah, it is. We're not done with it until today, so it's not due until Monday. 3.4 is due Monday. Okay. But you've got some representative problems that are due tomorrow also, don't you? Aren't there representative problems due tomorrow? Okay, so make sure you're on top of that. Okay, any questions? Okay, we'll give you a second to find them. Okay. Okay. So what we're mixing here is we're mixing some trigonometry in with our calculus. So 3.3, number 33, says f of x is equal to x plus 2 sine of x. And the reason they have problems on here, again, there's a difference between somebody that can just blindly go through and find derivatives and somebody who actually understands what they mean and then can apply those in a different setting and can pull in, again, all that information about algebra, trig, stuff like that. So on this problem, it says, for what values of x does the graph have a horizontal tangent? Well, let's think about horizontal for a second, okay? And for some people, depending on how long it's been since you had, a basic algebra class, horizontal, like this, slope would be 0. So in other words, we want the derivative to equal 0. So let's find the derivative. So in this particular case, f prime is going to be 1 plus, this is just going to be 2 cosine x. Okay, are we using a chain rule on this or anything? Technically, what rule did we just use for this one? Power rule. And what rule did we just use for this one? Yeah, we used the derivative of the sign, so we used a trig derivative right here. But what about the 2? What's that rule called again when you just kind of get to ignore the constant out front? Constant multiple rule, okay? We apply that rule without even really thinking about it, okay? So that's the derivative, and what we want to know is, when does the derivative, so the calculus is over at this point, when does this derivative equal 0? So when does 1 plus 2 cosine of x equal 0? Move the 1 over. Negative 1. Divide both sides by 2. So the question here is, when does the cosine of x equal negative 1/2? And there are a couple different ways that you can solve this. So we could draw a triangle for this, and we could think, okay, this is the adjacent, and this is the hypotenuse. Or if you think of it in terms of x's, y's, and r's, this is the x, and that's the r. So if I draw it on the xy plane, let's see, the adjacent side, that's the x coordinate. That's got to be negative here. So this would be negative 1, and this would be 2. This would be radical 3. So that makes this the long leg of a 30, 60, 90. This is a 60-degree angle. How big is this? 120. Okay, but we certainly wouldn't answer in degrees. Again, calculus is all done in radians. If you do it in degrees, my gosh, it's an absolute nightmare. Okay, so this is going to be 2 pi thirds. That's one answer. Is that the only answer? It's not the only answer. We can take this triangle and we can flop it down here. That makes this negative radical 3. This is still 2 because remember the radius is always 2. That reference angle is still 60 degrees, which means we've got 180 plus another 60. We're at 240 at this point, or 4 pi thirds. Are those the only answers? No, we take each one of those and they repeat. So this one right here, I get the exact same trig value if I go around full circle. So what we do is we say this would be 2 pi thirds plus, that's where it starts, and then 2k pi. And then the other answer would be 4 pi thirds plus 2k pi. Remember that stuff? Yep. Okay. You could also use a cosine inverse, but you'd have to know that your calculator would only give you answers in quadrant 1 and quadrant 2. You'd have to know how to find the one in quadrant 3, and you'd also have to know that it repeats. You can also do this. Think about what the cosine graph looks like. Looks like this. And where does it hit negative 1/2? Right here and right here. So guess what those points are? This is 2 pi thirds. This one is 4 pi thirds. And then you can see that this one repeats right here. This one repeats right here. So it hits negative 1/2 going down right here and again right there. I mean, that horizontal distance needed to repeat those answers or repeat that cycle is the period for the sine or the cosine function in this case, which is 2 pi. Yeah. Okay. Oh, let's see. When does it have a horizontal tangent? Let's see. Okay, what does it say? Because I think we did this one right. What does the book say?
Yeah, that's what I got too.
What does the book say?
So it says, parentheses 2 plus 1 times pi plus or minus 1/3 pi an integer.
Okay.
You got that.
Okay. Well, let's look at this. So this list is going to give us, and if we write this in terms of thirds, so this is, I mean, this is a little bit overkill at this point. And that's one of the things that's tough about trig is there are lots of different ways to write answers or arrive at answers. So let's write this in thirds. I'm going to write this as 6 pi thirds. So the next one, so one of the answers that comes out of here is 2 pi thirds. Then the next one that comes out is 8 pi thirds. And the next one that comes out is 14 pi thirds and so forth, right? Okay, the answers that come out of here, again, I'm going to make that into thirds. This is going to be, well, let's see, 10 pi thirds. After that, we're going to have 16 pi thirds. Doing okay? Then 22 pi thirds, and so forth. Those are just going to continue. So is it possible to write those as one single set like they did right here? So let's plug in some numbers here. It says it can be any integer we want. So let's plug in a 0. 0 is an integer. You plug a 0 in, you get a 1, right? Okay. So you get pi plus pi thirds, and you get pi minus pi thirds. So that gives us, let's see, that's 4 pi thirds here, and this is 2 pi thirds there. Okay. They're writing it down as one single one. It gives us the exact same answers. Does anybody see what they're doing here? I actually have a picture on the board that explains why they did it that way.
Well, how did they get
That's what we're going to talk about. Okay. Can anybody see what they did? Let me do one more. Let's plug in a 1. You plug in a 1, what do you get out of this? You get 3. 3 pi, and then you add pi thirds, and then you subtract pi thirds, right? So this is going to be, let's see, in thirds, that's going to be 9 thirds, so this is going to be 10 pi thirds. 9 thirds subtract, so that's going to be 8 pi thirds. Those are the same answers that we got up above, right? It's the same list. Pi, 3 pi. What's the next one if I wrote that down? That one? No, not 6 pi. 1 pi, 3 pi, 5 pi. Okay? This right here will count by odd numbers. Plug in any integer you want. It's going to times it by 2, which would make it even. Then it's going to add 1. If you take an even number and add 1, what do you get? You get an odd. So it's going to go through all the odd pi's. Where are all the odd pi's? This is 0, this is pi, this is 2 pi, 3 pi, 4 pi. All the odd pi's are right here. So they're saying, look, start right here, and then what does the plus or minus do? Yeah, the plus pushes us forward pi thirds. The minus backs us up pi thirds. So we land right where we need to be on the 2 of those. Now, would I write it that way? Probably not. Okay. But can you understand where they came up with that? Okay. Yeah. On what page? 3.3, number 42. Okay, so this is the limit as theta approaches 0, cosine theta minus 1 over the sine of theta. The first technique we'd probably try on something like this is, can I do it by substitution? And the answer to that is no, just like it's going to be on every one. Otherwise, these would be really easy. Okay, you get a 0 on the top and a 0 on the bottom, which we know sometimes we get a number answer for it. Sometimes we get 0, sometimes we get 1/3 or whatever it happens to be. Okay, and sometimes it doesn't exist. So what we want to do is we want to look at that one and we want to think about the techniques that we went over, some of the familiar limits, and how could we make this work out? Hang on. What's that? Okay, we could try and multiply by the conjugate. That would be one thing that we could do. We could try that. That would give us a cosine squared minus 1 in the numerator, and then we'd have a sine, right? So the top would be cosine squared theta minus 1, and the bottom, I'm going to leave it just in this format right here. So this is going to be cosine of theta plus 1. What is this right here? Okay, that's going to be a sine squared, right? Or is it a negative sine squared? It's a negative sine squared, okay? So this would be negative sine squared theta over the sine of theta, and then I have a cosine of theta plus 1, and I can cancel this one with that one. So that's gone and that's gone. So here's what I've got. Negative sine of theta over cosine of theta plus 1. Now, in this format, what have I done here? Now I can plug in the point of interest. I couldn't before because this was a subtract. So I realized, well, if I can make this a plus, I can turn that instead of a 0, if there's a negative in between them, I can turn it into a, what does it turn out to be here? A 2 in the denominator. And the numerator happens to be 0. Is this okay? We get a number for that. 0 divided by a number, as long as it's not 0, we're totally fine with. The answer to this is 0. Is that the only way to do that problem? Okay. If we do this another way, this can actually help us on a problem that's a little bit later. Here are some familiar limits that we know. As that approaches 0, the limit approaches 1, as theta approaches 0. And then we had this other one, theta minus 1, or cosine theta minus 1 over theta. That approached 0. Okay? So it's pretty close to that. I've got a cosine theta minus 1, but I don't have a theta in the denominator. And I've got a sine, but I don't have a theta in the denominator. So Weston, what do we do with this? Let's take the top and bottom and do the same thing to both. Let's divide them both by theta. So cosine theta minus 1 over theta, sine of theta over theta. And I go from something that I can't evaluate to another equivalent expression that I can evaluate in the limit. In the limit, this turns into a 0. In the limit, this turns into a 1. And just like this case over here, both of these are nice, clever methods of doing this problem, and they both get us the exact same answer of 0. Okay? But that's a pretty cool technique right there. Okay? So put that in your bag of tricks. Anything else? Quiz tomorrow is all derivatives. No limits, just derivatives. This stuff could show up on the test for chapter 3. Okay? All right. Anything else? All right.
How many problems are you in?
5 problems on the quiz. Say that again? Yeah, but I'm not, 2.8 was using the limit of the difference quotient, and I'm not going to have you do any of those. So basically 3.1 through 3.4. That makes you happy, huh? Did you have another question here, Alan?
I was wondering if that's something.
What stuff? No limits and no finding the derivative from the definition. Just, I'm going to give you a bunch of functions, you find the derivative. Yeah, applying the rule. Let's hope it's simple.